It's almost time. I think the clock in the back is a little bit delayed. Can you guys hear me? Good. I think I need to hold the mic like this in order to propagate the sound. So my hand is actually collecting the sound wave a little bit better for the mic. All right, so announcements for this week. So W3, and by the way, welcome to week 3. So we are only 1 week away from the first exam, by the way. Okay, so there'll be a reminder. There'll be a reminder coming next week. All right, so lecture ep5 is now being broadcasted live right here. And gentle reminder, there is a programming assignment due the end of the week, and this time is PA2. Now I've seen that many of you have already started working on it, running into problems. So in case you run into any problems, make sure you come to the PA2 channel. I think some of the problems you run into might have been addressed. Okay, so any questions regarding PA2? Yeah. So I think just recently, maybe yesterday. Yeah, I think yesterday, right? Okay, so one student was saying, hey, what happened to 42.161? Because in the videos, in the walkthrough videos, I keep saying, hey, connect to this server here. And the IP address in the video is 161. But this semester, we changed it to 221, all right? So every time you see 161, just assume that you need to change it to 221. So that's all the announcements we have this week. And in fact, starting from this week, the announcements will be kind of brief, given that you guys know how to work with the Slack workspace. You guys know about how to do the programming assignments and where to find the videos. And that's come back here, the lecture. And this is where we were, right? So there's not enough time, so we couldn't quite walk it through in class. But I see that many of you have already posted your solutions on Slack. Now, any one of you would like to speak about your solution in class now? And if you have any second thoughts after reading others' solution, okay? You have a change of mind on which one you like better. Circuit switching versus packet switching. Anyone? Okay, it's your time to speak. Oh no. Okay, I guess because you have already provided the solution, right? Your answer on Slack, and you probably feel less excited about speaking on it again. So it's okay. So let's skip the in-class discussion, all right? But I would like to bring up, most of you say that you like packet switching better. If you do, raise your hand. If your team says you like packet switching better, raise your hand. You see, yeah, most of you do, right? The reasons are, you like that packet switching allows more users, right? So the poor people still get access. Poor people like us students get access. Well, poor people like professors also get access. Right? What are the other reasons? More flexible. Yeah, you can send small files, large files without needing to worry wasting resources. What else? Have you thought about that there will become congestion on packet switching? And yet you don't mind. Yeah, and I see also students saying that circuit switching. If your team says circuit switching, please raise your hand. Oh, okay. So I guess those are the students who prefer having a reserved channel in the comfort of your own room to watch over video. Okay, watch the lecture over video. Good. And I guess, it's pretty clear that the car network, okay, the car network here is more like a packet switch network. The cars go on the road, and the cars kind of multiplex to each other in the intersections, right? And a lot of times we also run into traffic. Okay, in a car transportation system, we say congestion by saying it's traffic, okay, or traffic congestion. So similarly, in the data network that runs packet switching, we also have traffic, okay? Data traffic, traffic congestion, and train. Okay. This is quite characteristic that it's a circuit switch network, isn't it? Okay, on the track, you cannot having trains merging into each other. You kind of need to divide the time, okay, or divide the tracks, okay, having parallel tracks somehow, okay, to allow the trains running without colliding into each other. And trains are actually typically longer, especially the high-speed trains. But have you thought about the subway system? Or think about the metro system in Taichung or Kaohsiung or some part of Danshui. The train there, okay, on the metro system actually runs on the regular roads, right? There are intersections, and cars are actually interacting with the trains. So what kind of system is that?
Hybrid.
Exactly. Yeah, you do have hybrid, and packet circuits are running at the same time. Similarly, you can think about designing a communication network, a digital network with a hybrid like that. Okay, think about it, right? You can actually give priority to these trains that runs on circuits, while the packets or cars, I mean, they are already packet switched. Okay, they are experiencing already congestion, so it doesn't matter all that much. Okay, so user satisfaction cannot be worse if they wait a little bit more for these trains. All right, so that was the discussion I was looking for, and now we move on. And first, to summarize, packet switching and circuit switching. After the discussion trying to solve the quiz, what do you think? Packet switching versus circuit switching? Do you think packet switching is the slam dunk winner? Is data network Ethernet's way always gonna win? Probably not always, isn't it? It's great for short bursty data, right? Short amount of time but sending lots of data. Because it promotes maximum resource sharing, and it's quite simple, no code setup either. But on the other hand, we do have congestion. Packet delay might be unexpected loss, and probably worse. It could be packet loss. And so you need additional protocols, because of the way the very low level packet forwarding so we probably need extra mechanism at the higher layer to ensure data can be transferred in a reliable way if it's necessary. And what if we want to do some level of guarantee, for example, to do video streaming? Can we achieve circuit-like behavior with packet switching philosophy at a very low level? Can we do bandwidth guarantee? Well, people have been thinking about it, and this is still a problem that's not quite yet solved. And this is covered in Chapter 9, the multimedia networking chapter, later on in the textbook. And we unfortunately won't have time to cover this semester. Okay, at the bottom of the slide here, you see, is there any human analogy of reserved circuit switching behavior versus on-demand packet switching behavior? Right, we just went through quiz 3. That was an example of that. Oh, and by the way, I'm playing the audio out from HDMI. Is the volume okay for you? It's kind of low for me. Okay for you? No? Okay. Okay, mixed reaction. I think the part that might suffer is the students online. So let me just check them quickly. Hey guys, will you be able to? Okay. Yeah, Jingyuan was saying the volume is a little bit too small. The volume is a little bit too low. Okay. Let me see. So I tried to turn the volume up, but it turned out that there seems to be a maxima. Let me see if I can turn volume up from here, and that helps. No, the control goes off to the audio system. Okay, Jingyuan and the guys online, sorry about the volume being low. I will try to change back to VGA and try to take audio from the laptop the next hour, all right? So just bear with us this hour. The next few slides, they are still somewhat important, okay, but not strictly talking about packet switching, circuit switching, and computers. So these slides are to answer a couple important questions. We said that packet switching, what it does is to divide data stream into small packets. Why not large packages? Right? We didn't really justify that. We kind of like that L divided by R. The time it takes to send one packet is small because this is small. And in case the link is really fast, then this is small. But if this is a little bit larger, well, not so bad either, isn't it? Well, think again. And this is the example that I try to use to set up the stage. And it's just a slightly extended version of the previous example where we have two hops only, just one router between the source and destination. The packet size 7.5 megabits and the link rate 1.5 megabits per second. And you see that L divided by R is 5 seconds. And because you have three hops, so this time store 5 seconds for, store 5 seconds for, and 5 more seconds to store. Altogether, 50 seconds to send this packet L. Now, 7.5 megabits, large, right? Sending a large package like this over this 3-hop network, 50 seconds. Let's try dividing this large message into smaller packets and see how it will work. 7.5 megabits, let's divide them into 5,000 packets. This way, each packet is only this big, 1.5 gig. Link rate is still what? 1.5 megabits. So to send a small packet like this, it takes only 1 millisecond. Now, look at this. This is the same network, 3 hops. Each packet is now very small. And to send one packet, the first router will take 1 millisecond to receive it and then send it out. So 1 millisecond, 2 milliseconds, and only 3 milliseconds until the destination receives the first packet. And you know what? These links can work in parallel, right? Because router 1 here can be passing packet 1 while source start passing packet 2. You are trying to do also streamlining here, except that the unit of streamlining is a small packet. You see, why packet switching suggests small packets? Because it's trying to maintain the benefit of doing circuit switching. Unfortunately, we could not be streamlining bits. Okay. But let's keep the packet small. Then we get to keep some of these nice properties in the circuit switching. And having these links that can work independently is nice. We can pipeline or streamline the sending of the packets over the network. So each link works in parallel. The overall delay in the end is what? 5,002 milliseconds, only 5.002 seconds. If you recall earlier, if we send, okay, 5,000 small packets altogether, 7.5 megabits, each hop 5 seconds, and 3 hops 15 seconds. How much time are we saving? Big time, isn't it? This is why in packet switching, people always talk about cutting data into small packets. And why do we need to store packets first before forwarding it? Right? This is one of the reasons that we still need to form packets. Why we cannot just streamline the bits. The reason has something to do with how the routers is working. So inside the router, there are two key functionalities. Two of these. First is routing. So there's some sort of algorithms there. The routers, given the graph of the network, computes the shortest route. At the end of it, we generate a routing table like this, a forwarding table like this. And the way we look up this table is by matching the destination address, okay, of the packet. And so if a packet comes into a router, inside the router takes the destination address in the packet and look up this table. If there's a matching entry, the router discover what is the next router to forward to, what is the right direction to pass this packet further. You see, router what? Oftentimes well connected to other routers on the internet. So this router here could have multiple ways of passing the packets further. Unlike the very simple scenario there, each router has only one algorithm, right? So it's no longer that intuitive why packets need to be stored and then forwarded. Now you see, packets need to be stored here, and then the router can look up this field and match this entry, and then discover, okay, this packet is supposed to go out on network interface 2, this direction, to this router next. Similarly, this router needs to store the packet entirely, and then it can look at the header, this particular field, destination address, and find out in its own routing table which router next to forward the packet. Yeah, it's exactly because of the forwarding functionality that's required to pass data around over a packet switch network like internet. So, on packet switch network, we store packet before we forward it. So, forwarding here is to move packets to routers, all the way from the source, eventually reaching the destination. We'll definitely tell you more as we come to chapter 5. So in datagram network or in data network, the way it works is let's receive a packet entirely, okay, and look up the destination address to determine which is the next hop. And so you see, if the routing table changed, if the graph changed, routing table would change. When the routing table changed, when the forwarding table changed, subsequent packets might be following slightly different paths to the destination. Routes, packet traverse might change in a session, in a data stream session. So the analogy here is that the packet switch network is a little bit more like a regular car network. Okay? If you are driving a car, a lot of times, to find out the next segment, which road segments we should go on, we might actually stop and pause and ask someone for this destination, for direction, or park to the side and then look up Google Maps to find out which is the next segment. And actually, in the packet switch network such as internet, we can potentially emulate a circuit-like behavior that is called virtual circuit network. So instead of looking at the destination field in the packet header, we look at a very special header field called the virtual circuit circuit ID field. Okay, so there's a tag there, carries a number. Okay, that number determines which is the next hop. So inside a packet, it could be built in the packet header. One is called destination. There's another one called the virtual circuit ID. And one can look up that field and decide which is the next hop. And how do we do that? We'll talk about that also in chapter 4 and chapter 5. And what's nice about this approach is that we can then try to ensure all the packets for that stream traverse a fixed path. In a way, packet number 1, 2, 3, 4, chances high that they arrive in order. In this case, in case routes might change, if the later route is shorter than the earlier route, chances there packet 1 might arrive after packet 2. So, packet switch network. To sum everything up, this is general communication network. Two different flavors depending on which philosophy we design the core of the network. If we are going for a circuit core, it's called circuit switch network. If you are going for a packet-centric core, packet switch network. In circuit switch network, we know there are different ways of dividing resources into pieces. Frequency division or time division. But either way, it's very regular, following certain order. Things will need to be reserved. There's a call setup delay. It's good for long-lasting calls where you will prefer data not experiencing variation in delay, not experiencing losses. But this is very resource consuming. Each time we will not be able to allow many users going up at the same time. On the other hand, packet switch network, simpler, flexible, no idle resource, but we might have congestion. So that's the struct, datagram network. We look to the destination network address and then decide which is the next hop to forward. So we need to store the entire packet, so they might get queued. And they might get drew up in case there's not enough space in the queue. But we can also try to emulate circuit behavior using the virtual circuit tag, which allow us to look up into the packet header field a little bit faster and streamline the process more or less and maintain packet and byte orders. Packet switching versus circuit switching. All right, so that's pretty much all we need to talk about comparing packet switching, circuit switching. The last segment of video is a little bit long, about 10 minutes as well, but this one is more to give you a better sense of what real internet is like. Okay, so it's a more realistic view of the internet, and you see a little bit more of the structure, the machines in the core of the internet. Internet structure, it's a network of networks. Uh-oh. Sound volume really low. We learn we have end systems at the edge of the internet. They're connected to the core through the access networks, which are part of. But this is already maximum volume. I think the audio system here needs to allow us to adjust the volume higher. Okay, so there are actually two things we can do. One is to continue playing until it's the time for the break and I go to my office to fetch the VGA connector. Or I go now to get the VGA converter so that you guys will have an easier time and the guys over there online will have an easier time. Which one would you prefer? Now I go get VGA, right? Good. Guys, okay, so let's take a break for 10 minutes. It's now only 1:45. We'll come back at 1:55. Okay.
VLC player installed?
VLC now.
Because you can
Oh,
maximize the volume.
using VLC.
Yeah, like 2 times the volume.
Really, but
Yeah.
is it gonna maximize the volume of my laptop or the HD?
file.
Oh, the file. I see. Interesting. So you can tune the volume of the native video.
Yeah. But quick time.
But too late now.
Yeah.
Okay, I'll get the VGA connected.
可以把它们写进去。
然后标志用模板的话也不用，
所以你用完后，你有标记，不知道为什么都用上。
我去过国外店上面，还是说它是不能停止？
不知道，可是你之前不是也说你那时候在？
哦，对啊，
超可以。
然后他就是传递了这个，第二个
应该是这样。然后你 PS 是制作了？
没有，我只是正在做，我只是照着它的流程快速，我才跟到第2、第3个。
这个美好加一个数字的，会不会可以就是把这个然后在美好前面加个它的前面几间的叫读者输入之后，以后的档案里面，然后把以后档案那个图进来之后，在美好前面加一个因子，因此呢，好，就不成了，我只要一个加完之后再把美好的写然后过来。我觉得你。我没有这个，这个完全没有。 其实这一切是领导，原因是。那是下课了。我礼拜四是3点半才。这礼拜改，这礼拜是就是2点50到3点，因为这礼拜你说的。对。因为你说的，你现在是。刚笑。哦。啊，我在早上。礼拜四下。那就礼拜四上。你有没有觉得？我还没有过那。反正你可以，反正我觉得。所以你就命。我用伞的话也可以。对，就那个老师的推荐的。反正你可以直接在中央司那些，然后我们放在司仪前面。是可以。然后我就直接问，如果要学习，也没有。其实你也要帮他们出来做这种检测，因为好像有，那他有给你们比较多钱，因为你是检，然后他们会让注册自己的事，哇。打电完之后就可以直接在这里写。其实如果不行，我可能就把档案载下来，然后再电脑里，然后不要在手机上。 设置那个智能体，对，就是打乱了。去打别人。
Okay, good.
啊，有回到上设置。
All right, sorry for the prolonged delay. Took me a little longer to figure out the projector situation. I think I've worked it out. Okay, let's see if we can go back to the first 2 weeks and playing audio from my laptop.
Internet structure. It's a network of networks.
Better?
Earlier we learned we have end systems at the edge of the internet. They're connected to the core through the access networks, which are part of these access ISPs. Now, some of these ISPs serve home users more. They're called the residential ISPs. Others serve companies and universities. They are more often being called institutions and ISPs. Well, either way, any two hosts in these ISPs wanting to send packets to each other, their access ISPs will need to be interconnected. As a result, we see a network of access networks. Over time, they grow pretty large and complex. And much of these growth is driven by the economics, and some of it driven by governmental or business policies. In the next few slides, what you'll be seeing is essentially the evolution of the internet. What I'm drawing here is a bunch of these access ISPs, or I call access nets here on this figure. Let me just omit drawing the end systems because there's just going to be too much of them and the picture gets too messy. So the first thing the internet engineers are thinking is this: how are we going to interconnect these guys? Well, one obvious way is, how about connecting them all? But as a result, you see there are n squared connections. And when the internet grows, adding one more access net, we'll need to add n extra links. So this is going to be a very expensive thing to maintain. And so internet engineers go with the other extreme. Everyone connects to one global ISP in the middle. So data come here, and the global ISP transits the data for the access net to the destination. Similarly, here. So in a way, the global ISP in the middle here is providing transit services to the access nets, which are the customers. Now, as the internet grows, as the number of these access nets grow, then there will be more paying for the transit services. Gradually, the global ISP will begin to see profit. And when business is profitable, you see competitors. So now we have not just one global ISP, but multiple global ISPs. So A, B, C here are 3 global ISPs. They're competitors, but unfortunately they also need to collaborate. Because what? Just like the access nets needs to be interconnected so that they can serve the end systems, their customers. ISP A, B, C will also need to interconnect so that they serve their customers, the access nets. All right, so must interconnect. There are 2 ways for the global ISPs to interconnect. First is to establish peering links among each other. The other is to connect through these IXPs, Internet Exchange Points. Now these IXPs are special. They're typically set up by government fund or by the nonprofit organizations because it's kind of important that we have these, third company there maintaining the basic operation of the internet to avoid companies, commercial companies, to dominate. So that's pretty much the structure of the internet for a long time. But over time, we see more. So local communities such as this guy and this guy here can also grow. When there's enough number of these access nets around, we begin to see regional ISPs showed up. What these regional ISP is doing is this: offering lower price internet access to the access nets and try to negotiate internet access with the global ISP with a lower price. So hopefully the regional net here finds a margin of profit. So profit here and saving money here. For global ISP, this might not be a bad thing at all because it only needs to deal with one customer, which is the regional ISP, instead of multiple of them. Okay. So less overhead. And this structure has been there for a long time until about a decade ago. Content provider networks showed up. Let me talk about content provider network by example. So let me use Google here. It'll be easier for you to understand. So Google established these data centers worldwide. Okay. What they do is to go to access networks locally where the data centers are, and then ask to connect to the access network, their data center. Now, the number of machines they're maintaining there at their data center and the connections they're buying from the local ISP are actually comparable to the global ISP here. The entire infrastructure there at the content provider network is just as big as the global ISPs in the middle. But what's a bit odd is this. The content provider networks, they're actually physically at the lower level of the hierarchy. As opposed to the global ISPs, they are at the center of the hierarchy. Scale comparable, but where they are in the hierarchy, very different. All right. In the next picture, let me try to draw the network slightly differently so that you see where they are in terms of how resourceful these provider networks are. You see here then, the most resourceful one at the top, the least resourceful one at the bottom. So at the center, we have Tier 1 ISP and content provider network. Tier 1 ISP interconnect to each other through peering link, and they also connect to the IXPs. Content provider network somewhat different. They connect to the local access ISPs and IXP. All right. But keep in mind, this is not exactly absolute. Some Tier 1 ISPs might also have access ISPs connections. Google here, if this Tier 1 ISP offers a fair price, might also establish a connection. All right. Good. Now, the final slide is just to give you a rough idea what's inside a Tier 1 ISP. As I'm drawing here, it looks simple, but it's actually quite complicated. This is Sprint's backbone. Sprint is one of the major operators in the US. It's also a Tier 1 ISP. Each of these red dots is called a POP, point of presence. So the row there is pretty much like a data center in Google. It's a rack of machines. In this case, a rack of routers. Okay, so rack of these routers. They're interconnected between each other, and they are also offering connections to the customers. And some of them might be connected to other tier 1 ISPs. And these links are to go further up into the backbone, in the hierarchy of the backbone in Sprint's network. And this is internet structure, a network of networks.
All right, so you see, Google is now growingly almost like a ISP and a very high tier ISP. But if you think about it, that's not exactly far-fetched, right? Because the scale is just as large. And if Google connects to more access net and more ISPs, then it's pretty much playing the role of the major ISPs these days. And that concludes the core of the internet, finally. And we move on to the next subject. And starting from this point, I will be talking about a little bit of here and there, very general about the internet. And coming up, this is 1.4, the performance issues.
Starting from here, we'll focus our discussion mainly on the packet-switched internet. And 1.4 is to talk about the important metrics we care about designing protocols for it. That includes delay, loss, and something called throughput, which we'll talk about at the very end of 1.4. How do loss and delay occur? Well, let me draw your attention to the example below. That'll be easier. First kind of delay is happening here in the packet that is going out, being transmitted out. That delay the packet is experiencing is called the transmission delay. That is the time it takes to transmit the packet, and we know how to calculate, don't we? It's packet size divided by the link rate. But there's a second kind of delay experienced by packets here before they get to go out. These are what packets waiting in a queue, waiting for its turn. And how can there be packets waiting in a queue? It actually happens quite often when the incoming rate exceeds the outgoing rate. So you see in the example, A and B sending packets actively together into the router. In case the aggregated arrival rate is higher than the outgoing rate here, then you will see there will be always packet here waiting to be transmitted, and therefore subsequent packets will need to what? Wait up. And that is queuing delay these packets are experiencing. Now the calculation of queuing delay is a lot more challenging than the transmission delay. It really depends on the arrival pattern before a packet comes into the queue. Okay, now if that pattern is reoccurring, predictable, then it will be easier to calculate this. Otherwise, very challenging. Now, that explains packet delays, where they might occur. Packet might get lost as well at the router, and it happens here. Focus on this thing here. It's the packet queue. The size of the packet queue is limited. Okay. By the way, that packet queue is also often referred to as the buffer. Okay. And the buffer space is limited, just like the memory space is limited. The buffer space is just a way of calling the memory reserved, okay, to store these packets. Now, given that the amount is limited, in case congestion persists for a long time, then eventually you run into the situation. There's no longer free buffer space in the queue. In that case, arriving packets will get dropped, and therefore we see packet losses.
All right, so I hope that was clear where delay and loss occur. And now we focus and talk about delay. And this video is also quite long. 15 minutes, but this is talking about a very important performance metric, the first one called delay.
Now, packet delay. There are 4 components. The first component is the nodal processing delay, but we just call it processing delay. It occurs right here when the packet arrives at the router. Router here checks the bit errors in case there's any, and decides quickly which output link the packet should go out. Next, queuing delay. That's the time the packet waits until it's turn to go out on the output link. It occurs right here at the buffer space where packet queued up. But the amount of wait depends on the congestion level of the router. Component 3 is the transmission delay, and it's calculated this way. R being the link bandwidth, L being the packet length. And the time to transmit the packet out will be L divided by R. And it's happening right here at the interface between the router and the link. Final component, propagation delay. Provided the length of the physical link and the propagation speed of signals traveling the physical link, we know that the propagation delay is D divided by S. So essentially, the time for the packet to traverse the physical link. Be careful. S here is the distance the signal can travel per second. R here is the number of bits the transmitter can push out per second. Although I call S the propagation speed, R the link speed sometime, but there are 2 very different quantities. Right? Now let's go through a couple examples to exercise calculating transmission delay and propagation delay. What you're seeing here is a caravan of 10 cars. Now the way to think of this scenario is this. Think of cars being bits and caravans being a packet. So we have a packet containing 10 bits in a sense. The cars will be propagating at the speed of 100 kilometers per hour over 100 kilometers reaching the second booth. Toll booth number 1 here takes 12 seconds to service the car. All right. Question here is asking how long until the packet is lined up before the second router. All right, so transmission delay plus the propagation delay. So what is the transmission delay? We have 12 seconds serving per bit, and then there are 10 bits. So the time to push the entire caravan out of the toll booth is 2 minutes. And then the propagation delay is for the car to travel 100 kilometers. So 100 kilometers dividing the propagation speed. So we have 60 minutes here. And so altogether, 62 minutes before the entire caravan to reach the second toll booth. So you see, in this case, transmission speed, very fast. Propagation speed, slow. In the second example, the configuration is slightly different, mainly propagation speed and transmission speed. Propagation speed now goes really fast, but transmission speed much slower. So, question here is asking, will the first car arrive at the second toll booth before all the cars are being serviced? Let's see. When will the first car arrive at the second toll booth? So transmission delay, 1 minute. Propagation delay, so we have 100 kilometers, but we're traveling 1,000 kilometers, so we'll be spending 1/10 of an hour propagating, and that's 6 minutes. Together, 7 minutes. So the first car will spend 7 minutes before arriving at the second toll booth. Now, 7 minutes is also the time to service 7 cars for the first toll booth. That means we have 3 cars that are still behind at the first toll booth. So yes, okay. When the first bit arrived at the next router, there could still be bits not yet transmitted out from the previous router. So in this case, where the propagation speed is really fast, transmission rate very low, you had this weird situation. Good. Let's sum up packet delay. So there are 4 components: processing delay, queuing delay, transmission delay, and propagation delay. Transmission delay, very low, typically microseconds.
Well, I actually meant processing delay, very low, typically microseconds. Because I've recorded almost 10 minutes, right? And suddenly saying something wrong and it's too late to correct.
We just, ignore the processing delay when we calculate packet delay. Transmission delay, propagation delay, very easy to calculate. L divided by R, this quantity is often significant and especially the case for low-speed links. Propagation delay is slightly harder. It varies quite a bit from microseconds to hundreds of milliseconds. So this extreme is for satellite links, for example. We've seen earlier, it could go up to 200 or even more milliseconds. Sometimes the transatlantic or trans-Pacific links, very long optic fibers, could also take up to 100 milliseconds. Now, in the process of calculating packet delay, the hardest component is this, queuing delay. Now, it's very hard to calculate accurately because it depends on the congestion level at the router. Just to give you a sip of how hard it is, let's define again, R being the link bandwidth, L being the packet size. Let's add one more variable, the average arrival rate. So L multiply A is the average bit arrival rate. That is also the incoming traffic rate. R is the outgoing traffic rate. So we could define traffic intensity being LA divided by R. So when that quantity is close to 0, that means incoming rate very low, outgoing rate very high, then no bits really need to wait. So queuing delay very small. And it's depicted here. When LA divided by R is very small, queuing delay also very small. The other extreme is here. When the intensity is greater than 1, that means there are more bits coming in than more bits going out. And when time goes on and on and on, the newly arrival bits will need to wait longer and longer and longer. And it's pretty much here, approaching infinity. Now, when the intensity is between very small to 1, delay is simply growing. And as we will be approaching infinity, you see that the curve grows quickly like that, okay? Close to an exponential trend. So, hard to estimate queuing delay. In fact, it takes a whole semester for a professor to teach about how one calculates queuing delay. And at the graduate school, there's advanced queuing delay that one can also take to make sure that you do a better job. Okay, estimating queuing delay for highly dynamic incoming traffic.
Okay, so let me just take a pause there, just to be cautious. Like usually, it requires that the traffic is arriving at a certain pattern that is describable in mathematical equation. Then you'll be able to come up with a closed form to calculate the queuing delay. If the arrival pattern is somewhat very chaotic, it's still very hard to estimate the queuing delay, even if you take queuing theory at the graduate level. Okay, let's continue.
All right. So that was the theory part of the packet delay. One can also find out what is the real internet packet delay by trying out this program. trace route. Okay. What it does is to measure delay from a source one hop at a time all the way to a destination. So this is what I'm drawing here. Source to destination, and it's sending 3 packets one at a time to reach each of the routers along the way. So router there receiving such a packet would return by sending a reply back to the sender. Now the sender there can time the interval between the transmission and receiving the reply and gets one estimation of the round trip time between the sender to the router. So it works like this. 3 probes to the first router, 3 round trip time estimation. 3 probes to the second router, 3 round trip time estimations to the second router. And this goes on and on until it reaches the final destination, and then the trace route program stops. The output of the program looks like this. This is an example. Trace routing from Gaia, UMass.edu to Oricom, France. So this is saying first hop router's name is CS-GW at IP address 128.something.something.something. And there are 3 round trip time estimations, 1 and 2 milliseconds respectively. What's a little bit interesting is between hop 7 and 8. There. You see, at hop 7, round trip time was about 22 milliseconds, but suddenly to hop 8, the delay is about 100 milliseconds. So that is the transatlantic links connecting from US to Europe. A little bit more interesting is also hop 17 and 18. You see stars, stars, stars. That means the routers are not responding. Okay, and it could be because the probing messages are lost or the replying messages are lost. But it's more likely that the router is turned off replying to these. Routers are on, but the routers turn off replying these probing messages. Well, let's try, sending a trace route ourselves from here. How about that?
Okay, so this is Polly demonstrating trace routing physically from her MacBook.
Let's go over to a terminal and then trace route to say Google. How about that? All right. Good. First hop router. Well, it didn't tell me the name of the router, so chances high that the router doesn't have a name. Okay. Delay reasonable. 10 millisecond, 3 millisecond, and another 3 millisecond. Router 2 here, well, either the probing messages are lost or router turns off the functionality of returning to trace route probes. Now third hop, 30 milliseconds, suddenly much higher. Okay, fifth hop, delay not much higher than the third hop. And you see here, when it's star, 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 it takes longer time. It's because when the traceroute program sends the probing packet, there's a timeout interval. Traceroute will wait until the time exceeds the interval. Then it determines that, hey, the router is probably not going to respond anymore. So forget about the first probe, send the next probe. Next probe waits also some amount of time. Timeout, give up, and then sends the third probe. Okay, good. Finally, we reached www.google.com. But the name is actually quite different. TSA something something. Interesting. And the end-to-end delay, end-to-end round trip delay to www.google.com is about 20 something milliseconds. Now, something that's very odd is here. Hop 8. If you look closer, we do have 3 round-trip time estimates, but each time number A here along the way, the 8th hop, is slightly different. IP address is 101, 49, and 97. So you see here, packets, although going to the same destination, coming from the same source, as they go on the internet, the routes could actually change. Also, you see, hey, the time it takes to reach hop 5, 30 milliseconds, but the time it takes to reach hop 12 is only 20-something seconds. So the load of the internet changes also over time. So sometimes when you are probing to a closer router, could take a longer time because it was busier there. But when the traffic load drops and when you're probing a router that are farther away, you could get a shorter round trip delay. Very curious. And let's go back to the slide. And it turned out that it's a good time to start the next quiz.
All right. This is quiz 4. So if you go to the Slack workspace, you will see that there should be a new channel. Okay, recall how you discover a new channel and join the new channel. And this is quiz number 4. So this is again the trace route to oralcom.fr. Okay, and again coming from UMass, from a U.S. university. So Q1 here asks, how come? Okay, the 3 delay measurements are not quite the same. You see that for each hop, we get 3 round-trip measurements, right? So the first hop here returns 3 values. 1, 1, 8. How come the third measurement says 2? Okay. And if we look at hop number 4, the 3 measurements, 16, 11, 13 milliseconds. How come they're different? In Q2, how come some delay measurements to hop number 10 are longer than the delay to hop number 11? Hop 10 should be closer to the source, right? Supposedly the delay should be shorter. But you see, hop 10 here, the delay is 113, 121, but the hop 11, 113, 114, and 112, and never up to like 121. So round trip probes to hop 11 is actually shorter than to a router that's supposedly closer. What's going on? And now you're asked, can you estimate the delay between hop 3 and hop 4? So I'm not asking you to estimate the delay from the source to hop 3 or source to hop 4. I'm asking, can you estimate the delay between hop 3 and hop 4? Okay. Estimate the delay between, estimate the delay between hop 3 and hop 4, between these 2 nodes. All right. So this one should be relatively easy. And what about hop 8 and hop 9? Can you estimate the delay between hop 8 and hop 9? Okay, now the happy time begins. Find your teammate. Where are they? Hello? Okay, if you unfortunately fall asleep, okay, I know it's very easy for a class in early afternoon. All right, feel free to walk around. Okay, kick your legs, stretch, wake up. Okay, work with your teammates. Find out. What do you think? How come the 3 measurements are not identical? And what do you think? How come sometimes delay to a farther hop can be shorter?
是这样子的。
它那种是比较远的老板，然后时间段是那种常常换路种。
我觉得你有测试吗？这个好像会看样子，而且时间差。
我刚跑这个，我跑了大概30多秒。
人又是大的，也是有差。这种还是教育机构。
这是第一个会用，
其他的现象，然后这个也是，
它是每个都是看这个，
对啊，就像是他现在。从这里，然后扒到这里才到达。
应该是吧？它不是到最后的那个路径上没遇到一个啥？
对，每遇到一个路径就会停止，类似到这边才到。对。明明是照同样路径，你就。有一些变回应的应该就是在那个 process delay 那边就直接被砍掉。
What do you think? 没回应。That's one possibility. 也有可能。Either way, but if you see 3 of them all lost, chances high that it's just being blocked. Because there are not so many packet losses. But if you see only, hey, 3 readings, 1 loss, but the other 2 came across, definitely not that case. Chances higher, your case, packet drop. Okay. All right, guys, can I have your attention just for a little while? Okay, so we're still in the middle of the quiz. Okay, let me just have your attention for a little while. Okay, how about we try to answer Q1 first? Okay, if you hear others' opinion, it might be easier for you to derive your answer for Q2 and Q3. So Q1, how come the 3 delay measurements are not quite the same? What do you say? Have you reached a conclusion yet among yourself? Okay, good.
Maybe
James?
there are not only one path from not only one path to router I, so it may take different time to reach router I.
So there might not be just one route to a particular router. Yeah. So you see that in the demonstration I show, right? To reach one hub, they could be taking different paths. If they take different paths, very reasonable you see the readings are not exactly the same. Okay, that's a very good reason, James. Thank you. And James is, what team are you?
8.
Team number 8. Any other possibilities?
That there are different conditions when teachers were in the package. So while at the time that the road have maybe hard traffic and maybe they are busy, so it would be more delay.
Right. Right. What's your name?
Howard in
Howard?
7.
Okay. Team 7. So, guys, Howard is saying that, right? We are sending 3 probes to each router along the way. So when we are sending the first probe, hey, there could be some cross traffic and the volume is high, so delay longer. If the second time we probe, lower cross traffic, then lower delay. So the reason that from team 7 is saying that the 3 times we are probing, there could be a varying amount of cross traffic there. Okay, so that router there could be busy in different degrees. Therefore, the round trip delay we see being different. Any other possibilities? In the back?
It could be just like rounding error from the program.
Okay, that's very possible, definitely. Yeah, bug in trace route. Okay, or bugs in the router's reply. Okay, in the generation of reply. It could also be some time synchronization issue. Any other solutions? Possibilities? What is your name? Chen Bojun. Team number 4? Good. All right, now go back and discuss with your teammates a little bit more for Q2. Does that make it a little bit easier for you to think about why? Hub 11 delay is shorter than Hub 10's delay.
第一次在这边，它是塞着，但是等我从这里走的时候，它没有。
你说回传这边再到这边的时候，
就是虽然都是走经过，走这一次的时候，因为它这一次就是就前后走。
时间是算它回程的时候，还是送了3个？送了3个。他就接回来的时候，所以接回来的时候比较没有被吵到。
And so in case you missed the video, the way trace route works is this. From the source node, okay, on the left, the first group of probing goes to only the first hop. Okay, and it goes one after another, not in parallel. Okay, that's why you see the numbers being different. So when I say 3 probes, it's actually sequentially 3 probes, not 3 probes simultaneously. Now you probably see a little better. Okay, sorry for the confusion. The 3 probes, actually one follow another. After getting the first estimate, send the second probe. So they do not happen at the same time. Yeah, I know you guys are wondering, hey, 3 probes send out simultaneously, right? They should be experiencing the same level of congestion in case there's congestion in the first router. So the 3 probes are actually not happening at the same time. Okay. Okay, this is also first probe getting a measurement, second probe getting a measurement, third probe getting a measurement. Ah, okay, finally. All right, I think discussion is now getting calmer, meaning that some of you guys probably have a good idea, right? For Q2, what do you think? How? All right, student in the back. You have 2 reasons. Cool. Maybe.
First reason is
They may have different queuing delay because of the cross traffic. Great.
and second reason is up 10 and up 11 have different paths. For example, the first 2 up in upset 11 may be different from up 10.
Yeah.
So, just like their transmission time, the total amount of the transmission time of up 11 is different from
Right. The same reason.
up 10.
Okay. Good. Thanks for trying. What's your name? That's very cute, by the way. 谢维珍. Team 3. All right. Okay, so Wei Zhen here is saying, hey, same reason, right? For Q1, when we are probing hop 10, there could be traffic there. So there's more queuing delay. So the measurement is higher. But when we are probing now hop 11, traffic can suddenly be going away and delay ended up shorter. Another reason, just like I think Team A, James was saying that they could be taking different routes. When we were probing router number 10, it's a longer route, unfortunately. But when we are probing 11, shorter routes. Very good. But what about Q3? Have you started discussing Q3? How would you estimate the delay between router 3 and router 4? So where's router 3? Right here, right? Where's router 4? Right here. How do you get the delay on this link between router 3 and router 4?
猜测的状况是好的。
对吧？那现在更成熟，8跟9的话，8跟9的话，9还是没有。
因为我觉得8跟9比较像那种走或走嘛，
对，
都完全是完全没办法找答案。
A negative delay? A negative delay. Yeah, 9 and 10. 8 and 9, right? So would you like to try to answer for the delay between half 3 and 4?
Between 3 and 4, I think just average their
The 3 measurement, yeah. And then subtract. Okay.
But for 8 and 9, I think there may be different routes between the center
Right.
and destination. So
Right.
it can be measured. The 8 time between 8 and 9 might be measured.
Right, right. So based on this measurement, it's not possible to measure delay between. Very good.
So is it possible for the measurement? Is it possible for a measurement of half line that didn't pass the half edge?
It's possible.
Oh.
Yes, it is possible. Very good. Okay, so why don't we break Q3 into 2 parts? Okay, the easier one is the delay between hop number 3 and 4. Okay, do you have an idea? Okay, getting the delay between 3 and 4. Anyone? All right, again, student in the back, probably Xie Weizhen's friend, teammate.
You can use how to make this mark time minus half minimal time.
Oh, interesting.
Worst case.
Worst case round trip. Worst case delay. Okay, for the link. Ooh. Okay, so what is your name? Xu Shuwei. Are you also team 3? So Xu Shuwei is saying, hey, let's take the maximum delay from half 4 and the minimum delay of half 3 and use that to subtract one another to get the maximum delay, worst case delay between half 3 and 4. Subtract. Yeah, that will work as well, right? What is your name? Chen Jia. Okay, Jia Hong. 嘉是嘉义的嘉 and team 5. So how many of you thought about the same thing that Chen Jiahong is proposing? If you do, raise your hand. Okay, very obvious. What else? Not anymore. Oh, there's one more. Good.
Maybe we take the last one of half 3 and take the first one of half 4. So maybe the condition is much more similar.
Oh, very interesting. Right? Very interesting. How about we take the measurements that are very close in terms of time? Because the chances high the traffic volume are similar. Very interesting. What's your name? Oh, just 2 words. Team 3? Oh, wait.
Team 3.
Team 3. Oh, 3? Oh.
Team 2.
Oh, okay. So it's very generous of you giving credits to Team 3. Team 2, Shiwei, is saying, oh, okay. So internet traffic varies all the time, right? So if we do delay measurement, and somehow the measurements are far apart, then we could be measuring delay at the time where the traffic volumes are different. But if we take the measurements that are very close to each other, chances high that the two measurements are undergoing the same amount of background traffic. So you kind of cancel the queuing delay. Really nice. 思维. So it's a very typical technique we use to cancel noise as well. Anything else? Very creative. I love it. Now, how about the second part? Now, that part is challenging, right? So we have actually 3 solutions already for the first part of Q3. How about we apply these 3 solutions to estimate delay between hop 8 and hop 9? Let's see. Hop 8 and hop 9. What is the minimum of hop 8 delay? 104, sorry. And maximum of hop 9? 109. All right. Hey, subtracting the 2 values, we get 5 milliseconds. All right. Okay, possible. What about the second solution? If we take the average of the 3 measurements from hop 8, 104, 109, and 106. Sorry, someone has a calculator. Help me here. 106? And the average of hop 9? It does look like the average of hop 9 is a little bit lower than the average of hop 8, isn't it? But if we subtract hop 9's delay to hop 8's, we get a negative value. Yeah, so the average mechanism doesn't quite work here. But solution number 3, okay, if we take 2 measurements that are really close to each other, okay, hop 8, the last measurement 106, hop 9, first measurement 109, subtracting the 2 values, 3 milliseconds, possible. Nice. All right, so any other solutions for measuring the delay between hop 8 and hop 9? All right.
Only the positive value and calculate its average. For example, if we have 5 minus 7 and minus 3, only take 5 and divided by 2.
I see. So what you're doing is to do what? Pairwise subtraction first, right? In case the pairwise subtraction gives you negative values, then you exclude them, like you exclude outliers, because those are not possible. And you keep only the positive values and take an average of that. Okay, that's one way of doing it. Yeah. Anything else? Any other solution?
Yeah, we take average of all the classes we just mentioned.
Sure. Okay, so let me track the names. I think you are... Chen Jia... No? Oh, Chen Jiahong is you. Chen Bojun. Lin Bojun. Okay. Team number?
4.
Number 4. But you are a teammate of Chen Bojun. Oh, okay. There's one more. I think I see a hand here and there.
Take the shortest, so take the shortest in a hop and take the difference.
Okay. So you take the smallest value for each hop and then take the difference.
Because it's
Why?
more possible that the delays are the real delay by physical measures.
Okay. So you're Samuel, right? Team number 12. Oh, Samuel's idea is very interesting. So Samuel says that he will take the minimum of all the measurements. You see, as I tried to explain, right, in the delay measurement, the part that's varying a lot is the queuing delay. If there's no queuing delay, the delay will always be very small. Right? So if among all these measurements, the 3 measurements, we pick the smallest one, this is likely the measurement without condition. And then for each hop, you take the minimum and try to subtract. But in this case, it's negative, right? What's wrong?
Data is too small.
Perfect. In this case, chances high that having just 3 samples, not enough. Can you do more trace routes? Yes, you may. If you want to get a reliable estimation of the delay between hop 8 and hop 9, it will be very wise to try to repeat the experiments more times. Okay? Over a long time, take the minimum round trip time. All right, good, great job. And then we come back to the lecture. Okay? So let's try to wrap up 1.4 and give you a nutshell of 1.5, the next subsection.
Packet loss is a lot more straightforward. You see, it's because the queue is finite in capacity. So in case a packet arrives when the queue there in the router is already full. So you see this full packet here, will need to be dropped. That's why we see packet losses. Now, what we haven't discussed is this, the lost packets. To some application, it's actually okay to have packet losses. If it happened, let it happen. So we would not try to retransmit the packet at all. But in some cases, for some applications, users are expecting the messages arrive fully intact. Then we might need to retransmit. Now, as to which entity in the internet to try to do the retransmission, it's really up to the design. So in some cases, we might see the previous routers doing the retransmission. But in most of the cases, we see the original source, the source end system is doing the retransmission.
Loss is as simple as that. How you estimate the loss? Usually we check the packet sequence number. If there's gap, then there's a loss. Okay, and you divide it over all the packets that have been transmitted, you get the loss rate. Now the last metric, throughput.
Throughput is the third metric. And it measures this thing, the rate of transmitting data all the way from the sender to the receiver, from one end to the other end. And the speed of data is going through the entire channel, entire pipeline. Now, there are 2 ways of quantifying throughput. One is called the instantaneous throughput, the other, average throughput. Now, the units are both bits per second. Okay. But instantaneous throughput is more that you're measuring the throughput at a particular point in time. You will see that if you measure instantaneous throughput, it will fluctuate depending on the situation of the channel between the source and destination. But if you observe over a longer period of time, then you see that the average throughput is more or less stable. Okay, so the throughput here we're talking about and discussed throughout the rest of the sites will be more the steady state behavior, the stable average throughput, just to clarify. Now let me elaborate the example a little bit more. This is the sender, this is the receiver. The sender is essentially a file server hosting big files here. Let's say the file of F bits is being sent over to the client requesting the file. And so we're talking about just the file download, okay, not the request part. And connecting the server and the client, we have one link, one switch, and another link. So it's a 2-hop network. And the link capacity for the link directly adjacent to the server, is RS, and S here indicates it's the link to the server. And this guy here has the link capacity of RC, and C indicates this is the link rate for the link connecting to the client. Now, let's consider such a data pipeline as a fluid pipeline, water pipeline. Then you see I'm drawing the pipeline's width, the diameter, based on the link capacity, RS. So RC here, let's assume it's larger, then you see a bigger pipe versus RS, smaller pipe. And you can also think about the server here being a what? A water tank, dumping fluid into the entire pipeline here. Now, it might be a little bit easier for you to imagine, right? What is going to be the pipeline's throughput if you consider how the fluids will be arriving at the receiver effectively? Would it be RC or RS?
Too easy? Which one will be the throughput? RS or RC? RC? RS. Why? Okay, I'll explain why.
Well, it's probably not that hard, isn't it? Because the intuition tells you that, hey, this guy here, RS being smaller, will limit the amount of fluid that can travel through. Even though RC is bigger, the amount of water that will go through here effectively to the receiver is still RS. If it's the other way around, RS being larger than RC, there could be a lot more water coming in, overall carrying RS throughput, but this guy here being thinner is going to limit the rate of the fluids travel through. So in the end, at the receiver, RC is going to be the throughput.
And in the meantime, there's a flood here, isn't it? Because all these more amount of water gets stuck here. And that is what? Queuing. Water is queuing here at the switch. Or they could be dropped and flooded out of the system.
And this guy here and this guy here, the link on the end-to-end path with the smallest bandwidth is going to constrain the eventual throughput. So throughput here oftentimes is being called the end-to-end throughput to indicate that it's the rate of data being sent from the source, one end, to receiver, the other end. Well, after drawing the data network to a fluid network, you see that it's very intuitive how you derive the throughput from one end to another end. And those scenarios are very straightforward, just two links. Let's consider a case that's a little bit more like the internet, deriving the throughput for an internet-like scenario. So you see here, we have servers and clients, Data will be going from the servers down to the clients through the backbone, the internet backbone. So for each connection end-to-end, we'll be going through how many links? 1, 2, and 3. So we'll be taking the bottleneck link bandwidth as the throughput. So we'll be trying to get the minimum of the 3 segments. RC is this guy, RS is this guy, clear. The middle segment, well, if there are 10 links in parallel, then this middle link here, capacity R, will need to be divided by 10, as I'm assuming. The 10 connections are fairly sharing the entire capacity. So the throughput to be formulated is this minimum of RCRS and R over 10. In practice, however, nowadays on the internet, usually it's either RS or RC being the bottleneck. You see, this is an N system. This is an N system. We subscribe access to the internet through some ISP. So this, usually the rate is low. Just like this, the application service provider, they are also subscribing to their ISP. This is also low. As opposed to the big R here in the middle of the internet, in the backbone, those are usually large. It's just that nowadays there are a lot more connections sharing the big R. Okay, most of the time RC, RS are the bottlenecks, but occasionally you might also see when network is really congested, R is not quite enough to allow all the connections demanding services.
Right, so that was 1.4. Okay, the three metrics one used to measure the performance of the internet. And now we move a little bit further and to talk about something that's really not that technical.
1.5 Protocol layers and service models. Well, this is a very special section. There's not much really technical here, and the purpose is essentially to explain more. You'll see later in chapter 2, 3, 4, 5. The chapter's title is called Something Layer, Something Layer, Something Layer. Okay. We kind of talk about all these internet protocols or internet mechanisms by grouping them into layers. So chapter 2, we talk about protocols running in a particular layer. Chapter 3, another set of protocols running in yet another layer, and so on and so forth. So 1.5 here is to give you an idea why we kind of classify protocols into layers and what does each layer do in terms of functionality, making sure that the internet operates seamlessly. Okay, so we call that the service model, the internet's service model, or the architecture of how we organize softwares running on the internet.
All right, and that concludes today's lecture. I'll see you again Thursday. Any questions? All right, go. Still asleep? Okay, guys, bye. Oh, okay, I see Jingyuan solution. Send the probe. Okay, Yunxiang Q2. Ah, interesting. Good. Just so that you know, Jingyuan Yuanxiang, I've noted that you guys try to present your solutions. It's just that I miss checking the chat on the YouTube live. And let me end the stream for now.